Good day, everyone. Welcome to our presentation on learning Agile soccer skills for a bipedal robot with deep reinforcement learning one. Today, we delve into pioneering research that pushes the boundaries of humanoid robotics through deep reinforcement learning. This study not only tackles the dynamic challenges of sim-to-real transfer, but also enhances the robustness and diversity of robot behaviors in complex, multi-agent environments. Prepare to explore innovative methodologies and insightful results that could redefine the future of robotic agility and intelligence. Let's get started! Advancing deep reinforcement learning for Agile control, our research tackles the significant challenges of sim-to-real transfer in dynamic multi-agent environments. This is crucial as it pushes the boundaries of what humanoid robots can achieve, particularly in settings that mimic the unpredictability of real-world interactions. Our problem statement centers on enhancing the robustness and diversity of behaviors exhibited by humanoid robots. We aim to achieve this without relying on real-world data during the training phase, which presents a unique set of challenges. This approach necessitates innovative solutions to ensure that robots can operate effectively under a variety of conditions, further bridging the gap between simulated training and real-world application. Moving forward, let's delve into the key highlights of our methodology and the significant findings from our research. Our approach utilizes a two-stage training pipeline, which includes skill-specific training followed by self-play. This structure not only enhances the learning efficiency, but also tailors the development of skills that are crucial for dynamic interactions in a multi-agent environment. To bridge the gap between simulated training and real-world application, we've incorporated techniques such as domain randomization and system identification. These methods significantly enhance the robustness of our policies, ensuring that the robots perform reliably when transferred from simulation to real environments. Our findings have been quite promising. We've observed improved agility, adaptability, and robustness in the performance of humanoid robots. Moreover, our methodology has successfully demonstrated effective zero-shot transfer to real-world scenarios, where robots can perform without prior exposure to the physical world. These advancements mark a significant step towards the practical deployment of humanoid robots in dynamic and unpredictable environments. Embodied intelligence represents the pinnacle of robotics and AI research, aiming to create agents that navigate and interact with the physical world with the same agility and understanding as animals and humans. This slide illustrates our robot soccer environment, which serves as a testbed for our deep reinforcement learning algorithms. Here you see both simulated and real-world setups, highlighting the practical application of our research in dynamic, multi-agent settings. This environment not only challenges the robots to maintain stability and safety, but also to exhibit sophisticated behaviors like kicking, dodging, and collaborative play, pushing the boundaries of what autonomous systems can achieve in complex, real-world scenarios. As we delve into the realm of embodied intelligence, it's crucial to acknowledge the significant strides made through learning-based approaches, particularly deep reinforcement learning. This technology has not only revolutionized the control of simulated characters, but has also made substantial inroads into the physical manipulation of robots, showcasing capabilities that range from robust locomotion to complex interactive behaviors. Turning our focus to humanoid robots, we encounter a unique set of challenges. Unlike their quadrupedal counterparts, humanoids must manage a higher degree of instability and a greater number of degrees of freedom, all while ensuring safety. These factors complicate both the design and control algorithms necessary for effective operation. The core challenge we address in our research is the application of deep reinforcement learning for the agile control of humanoid robots within dynamic, multi-agent environments, specifically the context of robot soccer. This setting not only tests the limits of robotic agility and fluency, but also serves as a proving ground for the adaptability and responsiveness of our control systems. Our motivation is clear. Advancing the control capabilities of humanoid robots is not just an academic pursuit. It holds the promise of enhancing robotic performance in a variety of real-world applications, where dexterity and dynamic interaction are paramount. This research not only pushes the boundaries of what robots can do, but also expands the horizon of their potential integration into our daily lives. Moving on, let's delve into the limitations of previous approaches in the realm of agile control for humanoid robots. Traditional methods often rely heavily on domain-specific knowledge and manual interventions, which can be cumbersome and less effective in dynamic and unpredictable environments. This reliance restricts the adaptability and scalability of robotic systems when faced with new tasks or settings. Now, let's highlight the novel contributions of our study. We've developed a two-stage training pipeline that leverages self-play and domain randomization. This innovative approach not only enhances the learning process, but also significantly bridges the sim-to-real gap. By integrating these elements, our system can better generalize skills learned in simulation to real-world applications, paving the way for more robust and versatile humanoid robots. Diving deeper into our methodology, we've adopted a two-stage training pipeline that leverages deep reinforcement learning to enable agile control of humanoid robots in dynamic, multi-agent environments. A key feature of our approach is the zero-shot sim-to-real transfer, where we train entirely in simulation without the use of real-world data. This strategy not only streamlines the development process, but also mitigates the risks and costs associated with direct training on physical robots. In the first stage of our training pipeline, we focus on developing separate skill policies. These skills, such as scoring goals and getting up from the ground, are crucial for the tasks our robots are expected to perform. By isolating these skills during the initial training phase, we simplify the design of the reward functions and circumvent potential poor locomotion local optima. This targeted training approach ensures that each skill is robustly learned, setting a solid foundation for the subsequent integration and application in more complex scenarios. Moving into the second stage of our training pipeline, we focus on the distillation and self-play aspects. Here, the skills that were separately honed during the first stage, such as scoring goals and getting up from the ground, are integrated into a single agent. This process of distillation ensures that the agent can switch seamlessly between skills as the situation demands. Self-play then takes center stage, where the agent is pitted against a series of opponents generated from snapshots of its own evolving policy. This method not only tests the robustness of the agent, but also enriches its experience, leading to a more diverse and adaptive set of behaviors in dynamic game scenarios. Additionally, we employ domain randomization techniques to further enhance the robustness of our policies. By varying the simulation parameters, we prepare the agent for a range of real-world conditions, thereby minimizing the gap when transferring from simulation to reality. Simple system identification methods are also utilized to fine-tune the simulation parameters, ensuring a smoother transition to real-world applications. These strategies collectively contribute to the development of a more competent and versatile robotic agent. Moving on to the intricacies of our approach, let's delve into the reward structure and shaping that are pivotal in training our robots. We design specific reward terms to not only enhance the robustness of the behaviors, but also to ensure the safety of the hardware during real-world deployment. For instance, the upright reward incentivizes the robot to maintain a vertical orientation, crucial for tasks like soccer. Additionally, we introduced a knee torque penalty to prevent damage to the robot's joints, which is vital for longevity and consistent performance. Now, let's discuss the evaluation of our system, particularly focusing on zero-shot transfer capabilities. This method allows us to directly apply the learned policies from simulation to real robots without additional training. During our evaluations, we observed that the robots could effectively execute complex maneuvers like kicking and getting up, demonstrating the success of our training approach. These behaviors are not only a testament to the efficacy of the simulation training, but also highlight the potential of our methods for broader applications in robotic systems. Delving into the algorithmic backbone of our research, we've implemented a robust training process that significantly enhances the learning efficiency and effectiveness of humanoid robots. This involves a detailed step-by-step breakdown of algorithms, which are pivotal in training these robots to perform complex tasks in dynamic environments. The algorithms not only streamline the learning curve, but also ensure that the robots adapt to varying conditions effectively. Moving on to the key improvements and innovations of our method, we've integrated cutting-edge techniques such as self-play and skill distillation. These innovations are crucial as they allow our humanoid robots to learn and refine their skills autonomously, simulating real-world interactions. This approach not only addresses the challenges associated with sim-to-real transfer, but also enhances the robot's ability to perform agile control in dynamic, multi-agent settings. These advancements mark a significant leap from previous methodologies, pushing the boundaries of what's possible in robotic agility and adaptability. Turning our attention to the technical results, we've achieved significant advancements in the agility and adaptability of humanoid robots within dynamic multi-agent environments. The two-stage training process depicted here has been pivotal. Initially, we focused on training distinct skills, namely soccer playing and the get-up maneuver. Subsequently, these skills were distilled into a unified agent through a rigorous self-play regimen. This approach has not only enhanced the robot's performance in simulated environments, but has also demonstrated effective zero-shot transfer capabilities. Remarkably, when these robots were tested in real-world scenarios, they performed admirably without the need for further training. This underscores their robustness and the efficacy of our simulation-based training regimen. Moreover, the robots exhibited a range of behaviors that were both diverse and fluent, clearly surpassing what traditional training methods have achieved. This diversity in behavior is crucial for real-world applications, where adaptability to unexpected situations is key. Moving on to the technical results of our study, we've identified several key findings that underscore the effectiveness of our approach. Firstly, the use of self-play and skill distillation has been instrumental in enhancing the robustness and diversity of the behaviors exhibited by our humanoid robots. These techniques allowed the robots to handle a variety of scenarios in dynamic environments effectively. Additionally, we implemented domain randomization and introduced perturbations during the training phase. This strategy significantly improved the robustness of our policies, making them more resilient to the uncertainties encountered in real-world settings. It's also worth noting that our approach did not utilize any real-world data. We relied entirely on simulated data, yet this proved to be sufficient for successful sim-to-real transfer. This highlights the potential of simulation-based training to achieve reliable and effective robot behaviors without the need for costly and time-consuming data collection in physical environments. Turning our attention to the technical results of our research, we conducted ablation studies to dissect the necessity and effectiveness of each component within our training pipeline. These studies confirm the indispensable roles of skill-specific training and self-play. Skill-specific training allows for focused improvement on discrete tasks, while self-play introduces a dynamic and challenging environment that pushes the agent towards higher performance levels. Additionally, our findings underscored the importance of domain randomization and system identification in effectively bridging the sim-to-real gap, ensuring that our models perform reliably when transferred from simulation to physical robots. We also faced several technical challenges and limitations during our project. One significant issue was the sensitivity of our system to hardware malfunctions, such as joint calibration errors and the reliance on ideal actuator models in our simulations. These factors often led to performance degradation over time, highlighting the need for regular maintenance routines. Moreover, the operation time of our robots was notably limited per battery charge, primarily due to the high sensitivity of the agent's behaviors to battery levels. These challenges underscore the complexities involved in deploying robotic systems in real-world settings and point towards necessary improvements for future research. As we conclude our presentation, let's highlight the key contributions of our research. We've made significant strides in applying deep reinforcement learning for the agile control of humanoid robots within dynamic multi-agent environments. Our approach has successfully demonstrated effective sim-to-real transfer capabilities, which is pivotal as it eliminates the dependency on real-world data during the training phase. Furthermore, our innovative two-stage training pipeline, which incorporates skill-specific training followed by self-play, has significantly enhanced the performance and adaptability of our robots. This methodology not only refines the learned skills, but also ensures that the robots can effectively anticipate and react to the dynamic environment. These advancements collectively mark a substantial step forward in the field of robotics and embodied AI, pushing the boundaries of what these autonomous agents can achieve in real-world settings. As we conclude our presentation, let's reflect on the significant technical achievements of our research. Our robots have demonstrated remarkable improvements in agility and dynamic interaction within a multi-agent soccer environment. This advancement is largely attributed to our innovative use of self-play and skill distillation techniques, which have cultivated diverse and robust behaviors that clearly surpass those achievable with traditional scripted methods. Furthermore, we've made substantial strides in bridging the sim-to-real gap. The methodologies we employed have enabled us to successfully transfer trained policies from simulation directly to real-world applications without the need for incremental real-world tuning. This achievement not only underscores the effectiveness of our simulation techniques, but also enhances the practical applicability of our research in real-world settings. These accomplishments collectively mark a pivotal advancement in the use of deep reinforcement learning for controlling humanoid robots, setting a robust foundation for future explorations in this field. As we conclude our presentation, let's reflect on the key takeaways from our research. We've demonstrated that deep reinforcement learning is not only viable, but effective for controlling humanoid robots in complex, dynamic environments like multi-agent soccer games. This success hinges significantly on our robust training pipeline and the strategic design of reward structures, which are critical for bridging the gap between simulated training and real-world application. Looking ahead, there are exciting opportunities to enhance the realism and effectiveness of our models. Integrating real-world data into the training process stands out as a promising direction. This could potentially refine the behaviors our robots learn, making them even more adaptable to unpredictable environments. Additionally, optimizing our control systems to respond more rapidly could further improve the agility and performance of the robots, pushing the boundaries of what's possible in robotic sports and beyond. These advancements will not only push the field of robotics forward, but also deepen our understanding of embodied intelligence, opening up new possibilities for both practical applications and fundamental research.